In this video, I'm going to show you how we can create a Houdini pipeline that takes an asset with a bunch of different alpha cards and then converts it into fully opaque geometry. That new asset can be then imported and used in Unreal, and it has a very friendly rendering implementation with Nanite. So before getting into the tutorial, I want to go over one applicable use case on where you might find this helpful for performance. I've created this scene here in Unreal 5.4. It's using Nanite at 100% screen resolution, and all I've done here is taken an empty map and then scattered a foliage asset all across this level. Now what this foliage asset is right now is one that you would get from Megascans. It's using foliage that has a bunch of alpha cards. So we only have about 7K triangles here, but it's using a masked rendering mode. And why that's inefficient in Nanite is that when you use masked materials, it incurs a lot of Nanite overdraw and sort of interferes with the culling and rasterization in the Nanite Vizbuffer. We can verify this by entering the console command stat GPU, and this lets us look at all the different GPU timings for the current scene. Right now, the total time taken on the GPU is about 20 milliseconds, and you can see that about 4.5 milliseconds of it is spent for the Nanite Vizbuffer. What if, instead of using masked material, we instead ran a Houdini pipeline to convert all these alpha cards into geometry and then get an asset like this. So this is the same asset, but it's now using 77,000 triangles instead of alpha cards, which is a big increase in triangles, but it allows us to use an opaque rendering mode rather than the masked rendering mode. If we plug that into our foliage mesh here, and then check out the GPU timings instead, you can see that our total GPU time has dropped down to around 17 milliseconds, but clearly we've spent a lot less time on the Nanite Vizbuffer, only about 1.8 milliseconds. So big improvement there. Now, keep in mind, this is a super cherry-picked scene. I don't have world position offset enabled on this mesh right now, so that's another consideration that you'll probably have to use for foliage. But it does showcase that you might find some use cases where you'd actually want to convert assets away from using alpha cards into using opaque geometry. So now that we're actually in Houdini, I'm going to show you how to create a pipeline that I used to convert alpha cards into fully opaque geometry. The first thing that I'm going to do is I'm going to be referencing the attributes on our geometry a lot, so I'm just going to keep the geometry spreadsheet open for the duration of the tutorial. If you go to the top bar here, click Geometry Spreadsheet, and then if you go to the drop down here at the top right, and you can say Split Pane Top and Bottom, which now splits into two views, and I can keep the Geometry Spreadsheet open here at the bottom, and at the top here I can go back to Scene View, and now we can kind of reference both of them at the same time. I've already done a little bit of setup here to actually import our model and clean it up, but I'll run through what I've done super quickly here. I've exported a Megascans asset from Unreal and then imported it into Houdini. What you'll commonly notice is that when you import from Unreal, because the unit scale is different, you'll find that things are 100 times too large usually. So the first thing I always do is put down a transform node, and then under the uniform scale, I just scale it down by a factor of 100 here. And then if I click on the viewport and then hit space and G, I can now focus in on the actual geometry, and we're at a scale that's a lot easier to work with. The other thing to notice is that if we look at our vertex attributes, all of our interesting attributes are here on the vertex level right now. So like the vertex color, tangents, UVs, normals, and it's a little bit easier to work with them in the point level just because we're going to be doing a lot of attribute wrangles. So what I do is create an attribute promote, and then I take everything from the vertex class and then I promote it to the point class. So if you look at our vertex attributes now, there's nothing there. If we look at our points, now all that data here is on the point level instead. You can also see that there's some random FBX attributes here, like FBX rotation, scale, translation, which we're not going to use, and they kind of just get in the way, so it's a little messy. I put down an attribute delete, and I just deleted them from our point attributes, so we don't have to worry about them anymore. With that, we're pretty much ready to go here. The first thing we're going to need to do is to actually separate out our geometry and our asset to only process these alpha cards, right? This model includes both the bark and the twigs, but these are already opaque geometry, right? and we don't really want to be processing them. We just only want to be converting these alpha cards. In a lot of assets, they'll actually use different materials for the bark as they do for the leaves, and you could separate it out based off of their material path, right? But in this case, our asset is all using the same material, so we can't really do that. We need to separate them by selecting each leaf mesh individually, but that's a little troublesome. There's a better way to do it. If we go click on our viewport and then hit 5, we can see our UV view, right? And what you can see is all the bark and the twigs kind of have the same UVs here on the right side. And we can kind of select them all if we hit S to go into selection mode by clicking on the viewport and then hitting S. And then we can hit 2 to go select points, and we can just box select all of these points. From there, I can hit tab while still in the viewport and type in group, and this will create a new point group for just these points that we have selected. And then if I hit escape to go back into view mode and then hit 1 to go into perspective mode, we can see that selected all the points that are corresponding to sort of our bark geometry. So I'm just going to create this group name and call it bark. And now we can split this geometry into 2 different streams by creating a split node and then throwing it down here. And then we can split on any group that we have. We'll just split on the bark group that we created. And then I'm going to put down 2 null nodes to sort of show what we're working with here. So on our left stream of geometry, that's all of our bark geometry. And then on our right stream, these are all our alpha cards that we actually want to convert here. I'm just going to rename these nodes. They're a little bit easier to identify. Call that one bark. Call these ones leaves. So if we're going to convert these alpha cards into actual geometry, we're going to need to know their alpha texture that they're using in Unreal as the alpha mask kind of. And to import textures, what you can do is to use a cop network. So if we hit tab to create a new node and then type in cop2 network, this will give us a cop network where we can kind of do image and texture manipulation. So if we dive in here, we can create a new file node to import the actual texture. And then the texture is going to be the mask texture from Megascans, which I have here, the black alder mask. Now, if we want to actually look at what this texture looks like, we can go up here, and then instead of the scene view, we can go to the composite view. And here it actually shows the texture that we have. So I have imported it as a 1K texture. What this actually does in the Megascans material is that it's using the red channel as the alpha mask. And it might be a little bit hard to see because the green and the blue channels are used for other things. What we can do is create a channel copy node here and then plug that in. And just so we can see what this alpha mask is actually represented as, we can say that the target is the color and the source is the red channel. So what this is doing is it's copying the red channel into the every channel for color, basically. So now we just have a black and white mask, and this is what our actual alpha mask is. It's a little bit easier to visualize what it is, and I usually like creating a null node here just for the final output, and then I'll just call this something like out, because we're going to be referencing this later, and then we'll be easy to identify what this node is. So go out of this network back to our alpha to geometry, and then we're also going to go back to the scene view. So now we're working back in geometry. We need to take that texture and then actually create new geometry from it, right? And Houdini has a really nice tool for this. So if you type in trace to create a trace node, here we can take in a texture and then trace the outline of it into geometry. And you could import a file, but we used a cop network for it. So we're gonna say the input is a cop network, and then the cop path is what we just created. So if we go to alpha to geo, cop network, and then here's our output node. So we're gonna accept that. If we visualize this, what you can see, press space and G over the viewport, it's actually taken our texture and then created geometry from it. Now there's a few things we need to clean up here. The first thing is that it doesn't create holes very well. So you can see that there's actually a bunch of primitive errors here. If you go to the filters, you can say hole faces, which will now actually correctly identify where the holes are and create hole geometry for you there. So that fixes that error. The other thing you might want to do is that if we middle mouse click over this trace node, you can see that it already has 95,000 vertices, which is quite a lot, I would say. And to speed up processing time, we can actually poly reduce this right now. So we're going to create a poly reduce node and then just throw that in there. And then it's really kind of just up to your own quality standard of what you want to create this in. So you can say percentage of input point count, because when you do a trace node, it creates a lot more points than there are primitives. So we just go to percentage of point count, and then we will say percent to keep might be something like 30, if that still looks okay. Maybe even go a little bit lower to something like 15. You can see that it's kind of stripping away details now. So maybe we'll keep it back at 30. But now we've reduced the amount of vertices down to 27,000, which is a little bit easier to work with. Okay, so now we have the geometry for our alpha texture. We need to actually take these leaves and then convert them into the geometry representation that it has from the alpha mask. And the easiest way to do this is by processing each leaf one by one. So you can do that by typing in for each connected piece loop, and then throwing that in on our input. And then for the debug sake, I'm gonna go to our for each end and then just do a single pass right now. So it's only gonna loop over once. But now you can see that we're working with one individual mesh card, alpha card at a given time, and we can just convert them all one by one. So let's consider that the alpha texture that we just used is now in its UV space. Well, sort of. It's centered around 0, 0. So an easier way to do this is if you translate it and then just add 0.5 to the X and 0.5 to the Y. Now all this geometry is going from basically 0, 0 to 1, 1 in XY space. And our alpha card geometry lives in its geometry space, but we can move all of its geometry into its UV space by doing a very simple attribute wrangle. And if we throw that in there, we're just going to set the position of all of its points equal to what its UV value is. And what you'll see is if we go here, it's now totally flat on our XY plane, but if we template our alpha card geometry that we did, you can see that it perfectly overlaps with the actual alpha card that it uses. So if we want to convert this into geometry, it's a very standard Boolean operation, right? We can just take both of these inputs and then do a Boolean here and treat both of these as surfaces because they're totally flat right now. And what we're trying to do is take the intersection between them. So I'm going to take off the template here. But now you can see that the intersection between these two geometries is sort of what we want here for the actual alpha card. Now you might see that there are a few errors. They look kind of weird here. And these are because it's actually creating new geometry when you do this Boolean. So if we go to like our UV view, you can see it's a lot more obvious here. And we look at our UVs, all the new geometry, the UVs are kind of like initialized at 0, 0. So you get a bunch of these errors. And this is actually true for all attributes. If we look at like our normals, you can see some normals are completely pointing in different ways. And we're gonna need to fix this up before we really continue any further, just to clear up those errors. So the way we're gonna do this is to create a new attribute wrangle and then throw in our new geometry as an input, and then our original geometry here, the original leaf card, because this has all the existing attributes, as a secondary input. So when you think of, I'm just hitting 5 to go back into UV view. So we essentially just want to restore the original attributes that we had on this mesh card. And there's actually a really useful Vex function here called UV sample that we can use, where if we input a UV location, say something like right here in the middle of the card, we can sample what other attributes on the point level would be interpolated for that individual point. So say if we had something like right here and we want to find what the position of it was, we can call the UV sample on this geometry and then say we want to sample what the position attribute here is from UV space. And that's how we're going to correct all of the sort of attribute errors here. The first thing we're going to do is reset our UVs. These are a little bit broken because, as we saw, they're all kind of initialized at 0, 0. But because we're in UV space, we can actually fix this up pretty easily by just saying at UV is equal to our position now. And then if we finish that, you can see that all of our UVs sort of snap back into where their geometry position is, and now all of our UVs are fixed. In order to do it for all of our other attributes, color, normals, tangents, we actually need to loop over all of them and then sort of correct them in a similar way. So the way I do it is create a string names array, and this will include all of the attributes that we need to correct, right? So this includes our UV2s, the UV3s, the normals, both of our tangents. So we have tangent U as well as tangent V. And then as we loop over all of these, we're going to do a for each loop over each attribute name under names. And then we want to sample what that value was on our original geometry. So the function that I was talking about is to do a UV sample here. And this will give us a little bit of context here. The first input is the geometry that we want to sample the attribute from, and then it's the attribute name that we're trying to sample. And then we choose the UV attribute that it uses. Most commonly, this is just going to be UV, and then we actually give in the UV value that we're sampling from. So we're sampling from our first context geometry because it's indexed 0 to 1 there. And then we are trying to sample the attribute name that we want. The UVs that our original geometry was using was called UV. And then the actual UV value that we want to use is the new UV that we just corrected. So that's our sample. And then we just want to fix all of our point attributes by saying set point attribute on our new converted geometry from that same attribute name, and then on the same point number that we're iterating over, and then we're going to set it with the sample that we took from the original geometry. So that might have been a lot, and might be a little bit hard to see, but now if we look at all of our normals, they all seem to be corrected. If we look at our UVs, we corrected that one, but we can see like UV2s, are all fixed as well. The UV2s I think are actually like pivot painter textures, so they're all constrained to one spot anyways. But the one thing that we didn't do was let's just turn off all this debug stuff, is that we didn't actually restore the position of it. So this exists in the space of where our kind of bush was, right? So if we look at it there, this is still just a flat card in UV space. But the position is the same as any other attribute, right? So we can just add that on into our attributes that we're restoring. And now it snaps back to where the original mesh card was. And now we've kind of restored the position of it. There is one other small detail that I kind of left out here, is that we have an alpha attribute on our points as well. And because this isn't a vector, you can't actually use this section of code because it's using a vector. So we have to kind of copy this whole logic, and then just for the alpha, instead of doing a vector sample, we do a float sample. So I'm gonna sort of create this super fast, but say the attribute that we want to sample here is alpha, and then instead of calling this names, we can call this float names. Instead of iterating over our first names array, we're iterating over float names, and then it's the same thing that we're just restoring the alpha here. So that'll fix up the alpha attribute as well. And now all of our geometry is in the perfect way. Okay, so that's all we really need to do. And then we just plug in the output into the output of our for each node. And I'll create a null node here. And then just plug it in here and say this is the out node. Okay, perfect. So if we go look at it, we have to turn off the single pass right now, because right now we're iterating over just one mesh card. So we'll just turn this off, and now I'll do it over all the mesh cards. And what you can see here is at the bottom left, you can see the progress that it's making. So we have 1,144 mesh cards that we need to convert, and it's pretty slow, right? It's on pass 10 of 1,144, which is not great, and it's going to take you a long time. So I'm going to show you a faster way of optimizing this. So the first off, we need to know why it's slow. And the reason it's slow, if I just turn back on single pass here, if we look at the Boolean node and then we middle mouse click over it, you can see how long the last cook took here at the bottom here. And to do this Boolean operation, it takes about 1.5 seconds. So that's a long time. And if we have 1,000 different iterations, you're going to be waiting a long time. So it might be easier to just do this in a different way. The main problem here is that when we look at our geometry, to do an actual Boolean operation on this, we have a lot of intricate geometry here that we have to do a Boolean off of. So it can be kind of time-consuming, performance-intensive. We can kind of simplify this geometry that it actually needs to do by doing a for loop for each primitive on our polyreduce. And then we're just going to pack it into packed geometry. So throw that in there and throw that in there. And what this does is that rather than having a ton of different points for all of our different geometry, it's going to pack all of the primitives into a single point. So now we have, say for this one leaf, it's all just one point that has a packed geometry representation of that leaf. Then, before we actually do the Boolean, we can kind of call out all of the different packed geometry that we know is never going to actually be part of the Boolean. Because compared to like this leaf on top of the alpha card, we really only care about the geometry that it's overlapping here. So we want to call out all of the other different leaf geometry, so it just doesn't even get fed into the Boolean operation. Let's do that by creating another attribute wrangle. And then we are going to iterate over this new packed geometry and then just get rid of all the geometry that we don't want. So let's take that, and then as a helper input is our alpha card in the UV space. So now this is what we're sort of passing into the second spot input geometry here. And then we're going to iterate over all the points over this packed geometry. Remember that points actually correspond to a large section of geometry now. And then we're just going to say float distance is equal to the xy distance, which gives you the closest distance from a point to another geometry. So we want to find the distance to our alpha card based off of this point that we're currently iterating over. And then we can say if the distance of this point is less than 0. Something very small, something like this. So it's very close to the geometry. Or actually, let's say if the distance is greater, if it's a little bit farther away than the actual geometry that we look at, we can just remove the point from our geometry. And not the position, but that's actually ptnum. Okay, so now we just basically called out all the geometry that isn't really close to the alpha card that we're looking at here. And if we throw that into the Boolean instead, first we actually have to unpack this geometry because it's all packed geometry. Now, when you unpack it, it actually turns back into its normal geometry representation with a bunch of different points. And then if we do the Boolean here, we get the same result, but if we middle click over it, you can see that the cook time took 14 milliseconds. So it's extremely faster. And the actual time of doing this attribute wrangle, it's pretty negligible. Same with the unpack. So this is a lot faster to do. And to prove it, let's go to the output node here and then turn off the single pass and see how long it takes. So now of our 1,000 passes, we're already at pass 400, way faster. So we can actually kind of iterate and process different assets in a much more timely fashion. All right, so now it is done here. If we hit space and G, we can see that it's copied over all of the new geometry, and we've kind of converted these alpha cards into what we want. The first thing we have to do is to reintroduce our bark geometry, and that's pretty easy. We can just do a merge, throw that in there, throw our bark in there, and then if we merge it back together, this is essentially the new piece, this new asset that we created, and we can export that out. If we want to export it back to Unreal, we have to do a transform again. Put it in the transform, scale it up by a factor of 100 so it's in the units that Unreal expects, and then we can just do a FBX, ROP FBX output to export it as an FBX. And that's pretty much it to finish processing asset and converting alpha cards into fully opaque geometry. And this might not be the end of your road for whatever asset that you're working on, because if we throw down a divide node here to just triangulate the geometry, you can see that the final try count that we have here is probably very large. Yeah, it's like 500,000 primitives, which is a lot. And if you're doing things like world position offset, this might be a very significant factor for how you actually create this asset. So there may be other things that you need to do afterwards. It could be possibly going back to the poly reduction of your alpha texture and then either increasing the poly reduction, or I think an easier way to deal with this is to do an actual post-processing of your alpha texture before you do it here. So let's say if I went into my comp texture, if we look at our channel copy here in the composite view, the edges are very harsh. It's just 1 to 0. So instead what you can do is do like a blur here, and then just blur out the edges of it. So look at the result there. So now it's a little bit more blurred. If we go back to our scene view, whoops, hit box, but that's fine. If we go back to our scene view, you can see that our geometry is still kind of a little funky, but if we go to a trace, there's this threshold value that basically determines what value to trace the outline for. So if we set it a little bit lower, we can kind of extend the outreach of these polygons. So maybe a little bit more. That might be too much because it's taking a little bit longer to compute. But now we get a much more thicker outline of our geometry. And then if we reduce this to the input point count, we can probably do something even more drastic to something like 10. And this might be a little bit better depending on how close you look it up. This is only 8,000 vertices. So it should be, if we go back to our divide here and then let it reprocess, it should be a much more optimized version of this asset. Space G, and then we look at it. This one's only 100,000 primitives, which is still a lot, but it's sort of a game of give and take here, and then just finding the middle ground for what makes sense for your project. So I hope you found this video informative. I hope that you learned something. I genuinely thank you for taking the time out of your day to watch it, and we'll hopefully see you at the next one.